problem was with the glucose. So we're considering delta H and delta U for the combustion metabolism of glucose. Delta H and delta U. So let's take a look at some of this. Options. And so let's go to the fastest to slowest. The fastest would be the least accurate. The least accurate would be something like Petrucci, what he does. What Petrucci does is he ignores solids and liquids and just considers delta N of gas. And so if we want to figure out what delta U is we need delta H and W. Key to work. So we already have delta H. We just need W. Delta H is minus 2802.5 kilojoules. So if we look at delta N of gas is the moles of gas final minus the moles of gas initial. So we just total up the moles. At the end we have 6. At the beginning we have 6. So we end up with delta N of gas of 0. If the moles of gas doesn't change, so too the volume. So delta V will be equal to 0. And therefore delta H is equal to delta U. The other thing we could do is we don't ignore the solids and liquids. Solids and liquids are factored in, and for the gases, we treat the gases as ideal. And so we didn't do this yet, I think. And so what we'll do is we'll figure out V initial. V initial is going to be the volume of the glucose plus the volume of the O2. The volume of the glucose, I think we calculated that. It's 180.18 grams of glucose. The density is 1.54 grams per milliliter at 25 degrees C, 1,000 milliliters per liter. It came out to, what did it come out to? Did we already calculate this? 0.117. The volume of O2, we had 6 moles of O2. That was 24.7 liters per mole. This is at 1 bar and 298 Kelvin. It's the molar volume of the gas. Oh, what did this come out to? $148.2. So altogether, V initial is going to be 148.31 liters. Let's calculate V final. V final is going to be equal to the volume of the CO2 plus the volume of the water. The volume of the CO2 is going to be the same as the volume of O2 because they're 6 moles and they're ideal, so it's 148.2 liters. The volume of H2O, we have two choices. You know, we could assume the density of 1.00 grams per milliliter. This density is good to 2 decimal places here. And so we have 6 moles of water times 18.02 grams per mole. The milliliter weighs 1.00 grams, and then convert it to liters. So what does that come out to? 16 times 18.02, 0.108 liters. Or we could look up the density. You know, this is the density at 25. We know that the density of water changes in temperature. If we look at the density at 25 degrees C, I'll redo the calculation. The density at 25 degrees C is equal to 0.9970 grams per milliliter. And so instead, we'll just use that, 0.9970 grams. We would get 0.108 for liters. This comes out to 8. What was this one? It's 8.1. So the difference is like 1084 versus 1081. 1084 is more accurate, of course, because we're using a more accurate density. But the difference is not hugely significant. And so V final is going to be 148.3. Well, it depends on which density we use. What is it? 148.3. Like 148.30. We should have carried, or I should have carried more decimal places. The reason is was the change in volume very big? Change in volume is kind of small. If we use this as is, then delta B is equal to what? Delta V is equal to 0. But let's go ahead and calculate it. Delta V is equal to 0.01 liters. Looks like the initial volume is bigger, the final volume is smaller. And so volume is contracting. Work is equal to minus P delta B. P is 1 bar. Delta B we'll just do as 0.01 liters. And we get 0.01 liters bar times 100 joules per liter bar. And we get, it's 0.01 times 100 would be 1 joule. This is negative, so this is negative here too. So the work involved, the initial, oh actually the volume was, sorry, the volume is negative. So negative times negative gives us positive. And so we get plus 1 joule. So, Petrucci said, go ahead and ignore that plus 1 joule. Is 1 joule significant? No. Well, it depends on what you're comparing with. When you look at delta H's of combustion, they're kind of big. And so, you know, if you have a delta H of combustion of 2,800 kilojoules, 2,800 kilojoules is 2,800,000 joules. 2,800,000 joules, is 1 joule really going to make much of a difference? No. So this is why Petrucci says to ignore. He doesn't say to ignore because the work is negligible. He just says to ignore because the numbers are huge that we're dealing with. You know, it's like the difference between 1 and 3. Well, it depends on what you're comparing with. The difference between 1 and 3 can be significant, hugely significant. You know, and this is why you're worried about it. But you have to put it in the overall context of things, and that's a hard thing to do because you don't know, you know, the overall context of things. You know, because it depends on what you're comparing. And so, in this case, it is work. I mean, you still have to do it, but it's still fairly small. And so we do it, and rather than getting 28.0, what was it, 28.0? .2, is that it? Kilojoules, negative, we'd have to add the 1 joule. Well, 1 joule in kilojoules is 0.01 kilojoules. And so we add that and we end up with about 2805.1999, right? 1999. 19929, sorry, kilojoules. Did it change much? In other words, we're going to just end up with minus 2805.2 kilojoules around. And so delta U and delta H are the same thing. But then, you know, we didn't really do this calculation as accurately as possible. We could do it more accurately if we don't assume that the gases are ideal. And so let's see if that makes any difference at all here. And so we're going to complete the calculation, but in this case, we're going to assume these are real gases, not ideal gases. Then we're going to factor in solid and liquid as well. And so this would be a comprehensive calculation of this. All right, now we need to know the identity of gases. So, you know, here we have the glucose and the 6O2s. Down here we have the CO2. What was the volume of the CO2 that we got from yesterday? $148.11. And the volume of the H2O we just did, in liters, it was 0.108 liters. And so the total volume here is going to come out to 148.21 liters. That's our start. I probably should carry extra digits. The volume change is probably going to be small. All right, now we're going to do O2. You know, the volume of the glucose we did, you know, the volume initial will be the volume of the glucose. The volume of the glucose was, we just did that, but I erased it. It was 0.117 liters. Now the volume of the O2. Well, the volume of the O2, we're not going to use the ideal gas because we know O2 and CO2 are going to deviate from ideal behavior to different degrees. CO2 deviates more significantly than O2. And so let's go ahead and figure out the volume by using the Van der Waals equation. You don't have to have this memorized. You should know how to use it. calculating pressures with the van der Waals equation is not that hard. Calculating volume is hard because of this v squared in here. V to the minus 2. And so for O2, A is 1.382, and B is 0.0319. And so we just set it up like we set up the last one, and see if we can do this one faster this time. And so it's going to be 1 because it's 1 bar. And so it'll be n squared, which is the number of moles. So 6 squared is 36. 36 times A is 1.382. 49.752. So I get 49.752 for V squared. V minus NB, so 6 times 0.0319 is 1914. And we did this calculation earlier. What was it again? 148.74 was our target, correct? 148.74. So, you know, our first guess is going to be, let's guess V equals 149. We'll do the same first guess as we did last time. So V is equal to 149. Then let's see how many guesses we can get this in. So I got 49.752 divided by V squared, 149 squared. Plus 1 equals times 149 minus 0.1914. So I got 149 on the left, 0.14, and it's our target's 148.74. So it's a little high. What should we do for our next guess? Well, usually I just try to stick with, whole numbers, and then start adding decimals. I don't want to go too fine because, this is like when you're trying to focus something. First you do the coarse adjustment, and then you do the fine adjustment. Because if you start doing the fine adjustment and you're off, then you're going to be doing fine adjustments here, but you're still far away, so we're going to go back here. So I'll just do this just to see where we're at. 49.752 divided by 148 squared plus 1 times 148 minus 0.1914. So here we got 148.14, which is still not equal, but we're getting closer, it looks like, doesn't it? So let's take a look at this here. Between 148 and 149 we have, looks like 10, right? We go up 1 unit. Or not 10. If I just did this, it'd be 10. And so I want 7. I'm going to ignore the 4. And so I'm going from 81 to 91. And, well, actually, now I got to factor in the 4. So I'm going from 814 to 914, and I want to go to 874, which means that I need to go up 6 above this and 4 below this. So 6 above this, 4 below this would be, yeah, I think that, we're not going to go that fine yet. We'll just do 148.7. Let's try that. 148.7. And so 49.752 divided by 148.7 squared plus 1 times 148.7 minus 0.1914. 148.84. 148.84 is a little bit high. So what do you think for your next guess? 148.6. Let's try 148.6. So 49.752 divided by 148.6 squared plus 1 times parentheses 148.6 minus 0.1914. Guess what I came out to? 148.74. So we did it in 4 guesses. So how many guesses did the last one take? 6? 6 guesses. A lot.
Professor?
Yeah.
So do you actually have it for the bond and solve for that equation?
This one?
No, for that equals NRT one.
This one?
Yeah. Do you have it already like figured out somewhere?
Did I have it figured out?
Yeah.
No.
No.
No, I mean, actually, yes. The truth is yes. I figured it out because I already did this calculation with the morning class. In the morning class, it only took 3 guesses. This afternoon took 4 guesses. The morning class, just guessed 148.6, but I probably would have guessed 148.7. But the students guessed 148.6. So we got it in 3.
I mean, just the equation itself.
The equation?
Yeah.
The equation I just got from the book.
No, right. But I'm saying, do you already have it figured out for V?
Oh, you mean solve for V?
Solve for V, yeah.
Yeah. I don't bother. I don't bother solving this for V because it comes out to an equation like this. AB cubed plus BB squared plus CB plus D equals 0. So you get it in this form, cubic form. Like, this is like a quadratic equation. And then, do you guys know how to solve equations like this? Have you solved an equation like this in algebra? Some people have, yeah. Factor and graph, right? You graph it. Do you graph it? You look for zeros?
Or not based on x, no, based on ax, 8 times the x over, it's already complicated. So we don't know it's something like this, just basically.
You have a formula you plug it into.
Yeah, have fun with copying. And eventually I'll take well, especially when
Well, a lot of people say, what's the use of learning this kind of math? What's the use of learning this kind of math? Because we have calculators that can do it, right? But, there are certain mathematical things you have to know because the calculators, how many digits does your calculator carry in a calculation? Can you tell me how many digits your calculator carries? Well, I looked it up. Because your calculator can carry like 8 to 10 digits, usually 10 digits for the more fancier programmable calculators. And so a lot of people don't know, but what happens if you have more than that number of digits? Your calculator rounds off the number. And you can think of problems where the calculator will round off and the round off error is significant. Like the round off error is too big. and the answer comes out some ridiculous number. And so calculators aren't fail-safe, you know? In fact, when I used to allow programmable calculators, I would think of problems where the calculator would fail, you know? And it's not that hard, actually, to think of a problem where a calculator will fail without having to do some additional algebra. Excel will carry a lot more digits. I think Excel carries 100 digits. And so it would be a lot harder to make Excel fail. I wouldn't be able to do that. But, you know, nowadays, if you want to solve, you know, in your calculator, you just plug in A, you plug in B, you plug in C, you plug in D. I'll tell you, the Casio FX115 will do this. If you go to the Casio FX115 and you hit equation, then you can solve a cubic equation. And all you do is you plug in the A, B, C, and D. So you could have done this on your calculator. But if that's the case, then I would have to make this not a third order. I'd have to make it a fourth order, so it's impossible to do on your calculator, because somebody's going to tell me they don't have to do this because their calculator does that. And so I'd have to think of a problem that they can't do on their calculator, which isn't hard to do in Chem 1B. Chem 1A, it's more difficult because Chem 1A, there's just not that much math. And so this method of successive approximations, you have to use in Chem 1B on occasion, because we'll have sixth order equations, you know. You have a sixth order equation, how are you going to solve it? How do you solve it? Sometimes you can square root it, sometimes you can do other things. But oftentimes you can't. You just got to solve it for some answer. So do I have this? Yeah, I know the form of this. I have it somewhere. I've written it down, but I've never used it. Because, I mean, why bother even wasting time doing the algebra? Just use successive approximations. You know, I don't, you know, if you change the formula, you're still going to have to do the same thing. Now, doing successive approximations with a 0 on one side is terribly difficult. Because if you have a 0, what is close to 0? Is 0.1 close to 0? Is 0.001 close to 0? When am I close enough to say, oh, I'm close enough to 0, I can stop guessing? People do this with successive approximations. I saw one person set it up like this and then do successive approximations to solve it. It happened to be a sixth order equation, and they were trying to solve it to 0. And they got pretty close, right? But it turns out that is nowhere near close, because 0 is 10 to the minus infinity, right? And this is only 10 to the minus 7. They're way far off. Their answer was way far off too. That wasn't a good answer. And so don't change the form of this. Just use it as is. You never want to put a 0 here when you do successive approximations. It'll never converge. You do this in Excel. You know, if you want to get all fancy and trick Excel, you can program Excel to do successive approximations for you. You can find the programs that are online, and the problem is sometimes it doesn't converge. So it's just doing iteration after iteration and not converging. And then you got to kill it, otherwise you're never going to get an answer, and it's going to take forever. Or you can do a manual. You know, if I did this, normally I just do this in Excel manually. I could do it in like less than 30 seconds. You can get an answer, you know, easily. Well, let's continue with this here. So if we don't treat the gases as real, I mean, if we don't treat the gas as ideal, then we see a more significant volume change, I think. Let's see, what does this come out to? This is going to come out to 148.71. So we're going from 148.71 to 148.21, a volume change of about a half a liter. And so delta V, we're losing a half a liter. So delta V is equal to minus 0.5 liters. When we treated the gases as ideal, we gained a tenth of a liter. When we're treating the gases as non-ideal, here we're actually losing a half a liter in this reaction. And so here the pressure is 1 bar, and so the work is just going to be minus 1 bar times negative half a liter, and so the work is going to be plus 0.5 liter times liter bars. And then to convert that, the conversion is just 100 joules per liter bar. It's an easy conversion. And so this comes out to, what does that come out to? Is that right? Half a liter? This comes out to 50 joules. Now, is 50 joules significant or insignificant? Is 50 joules an insignificant amount of energy or a significant amount of energy? Is it, can I just ignore 50 joules? Is that okay? Let's ignore it. We don't care about it. 50 joules is nothing. Is it? Nothing?
It's something.
It's not nothing, right? 50 joules is not 50 joules is significant because 50 joules, if you have a cup of coffee, 50 joules could warm it up a little bit, right? A little bit, not much, but. Well, 50 joules, well, this is it. The only reason we're ignoring this work is significant. The only reason we're ignoring this work is because we know the other number. The other number is huge. The other number is on the order of millions of joules. If the other number is on the order of millions of joules, then 50 is. And so, getting back to an earlier question Sarah was asking was about the 1 versus 3. The only reason I say 1 and 3 are very close to each other is because I know the ultimate number. The ultimate number is like, 80, 100. If we're dealing with 100 joules, then the difference between 1 and 3 is like 2%. It's not so big, I think, in the overall scheme of things. And so it's because I know some numbers and I know what I'm comparing it to because it all depends. It all depends on what you compare it to. And so this is a significant amount of energy here. I mean, we're blowing up a half a liter balloon. You can't do it for free, right? It's going to cost you energy. But I know that when I'm looking at delta U is delta H plus W. And so delta H in this case is 2,805,200 joules. And so that's negative. Now I got plus 50 joules. And so that's going to give me, 2,805,150. So I went from, the 200 to 150. Is that a significant change? I think so. But in the context of 2 million, it isn't. And so the numbers, it takes time and you don't know, can you ignore it? Can you not ignore it? It depends. It's like if you have 10 milliliters of water, is 10 milliliters of water significant? Well, how can you say? 10 milliliters of water might be hugely significant on the surface of the Mars. 10 milliliters of water could be hugely significant on the surface of Mars, but on the surface of Earth, is it? And so this is what we do all the time. We look at significance, and the significance depends on the number you're comparing it to. So if you say, okay, 50 joules, what about 10 to the minus 19 joules? If I have 10 to the minus 19 joules, surely that must be insignificant, because 10 to the minus 19 joules is a minuscule amount of energy, right? And so is 10 to the minus 19 joules insignificant or significant? The answer is it depends on what you're comparing it to. If you're comparing it to a cup of coffee, will 10 to the minus 19 joules do anything to a cup of coffee? Absolutely nothing. It's insignificant, it's negligible, it's like zero, you know? But if you have a single hydrogen atom, 10 to the minus 19 joules is a huge amount of energy. Because 10 to the minus 19 joules is the amount of energy it takes to rip the electron off a hydrogen atom. That's it. And so, hugely significant. Anyway, we'll talk about numbers some more later, but you can see after all that work, did it really change the final answer here? No. And so basically, we really aren't going to deal. Although you can see that, you know, if we treated both of these gases as ideal, the volumes are the same, but we see there's a half a liter difference in the volume because one is less ideal than the other. For gases too, you know, when do we really worry about, you know, non-ideal behavior? And you have to do more calculations to see this, but instead what we'll do is we'll just summarize it in this graphic here. Basically, the ideal gas law, do you see this black line? That's the ideal gas law. If you look at the overall picture here, what you see is the ideal gas law is worthless, absolutely worthless. Because if I use the ideal gas law here to predict the CO2, I'd be way, way off. And so the ideal gas law is only valid right here. And it turns out it's valid here just serendipitously because the two errors cancel each other out. And here, the ideal gas law will give you a correct answer, but that's by chance. Otherwise, it's worthless.
That's only for O2 and CO2.
And H2 too. H2 deviates heavily from ideal gas behavior as well. The same with helium. Ideal gas law would predict this black line. And so everything's going to be an enormous error here, especially CO2. Look at that. Well, we don't really have to worry about that because when you look at the scale of this plot, you know, where it's really off here is about 100 atmospheres. Do we do much chemistry at 100 atmospheres? No. In fact, most of our chemistry is at around 1 atmosphere. Well, around 1 atmosphere is right at the start. Well, ideal gas law is okay there. From about 0 to about 10 atmospheres, ideal gas law works really well. But once we start going above 10 atmospheres, then we start seeing more significant deviations for these. That's with pressure. Pressure is pretty consistent. Temperature varies. You know, it depends on the gas. Helium stays ideal to very low temperatures, but steam, does steam stay ideal to very low temperatures? No. And so for temperature, you have to look at it case by case to see how far it deviates. And so if you're working with very high pressures like this or very low temperatures, you shouldn't be using the ideal gas law because you're going to have a huge error. You know?
You should be using van der Waals.
You should be using van der Waals or something else, right? There are other equations in addition to van der Waals. There's something called the Villarreal equation and others. All these are empirical. The van der Waals just, you know, the van der Waals is just taking a curve like this from experimental data and then fitting this to a polynomial function and then just adding adjustable parameters. The more adjustable parameters you have, the better. I shouldn't say, somebody asked me about polynomials this morning. But polynomials, we try to avoid fitting things to polynomials because polynomials don't, unless it's empirical, because empirical equations just has to fit the curve. It doesn't have to have any physics or physical interpretation. And so this is why we try to avoid polynomials, because polynomials you can fit any curve as long as you have enough parameters. But then it starts to deviate from the interactions. All right, so once we have our delta H, then we can use our delta H's. In this case, delta U and delta H are very similar. And so if you did have an iron stomach in which the volume did not expand, you would have gotten the same amount of energy here, you know. Well, just slightly less energy. Just 50 joules less energy. Right? Slightly. If you had a whole mole. So in science, we often make compromises in the calculations. We lose a little bit of accuracy, but what we gain is speed. We can gain a lot of speed. And how much accuracy do we lose in this case? Very small. All right, I want to move on to chapter 8. Chapter 8 deals, the first part of chapter 8 is electromagnetic radiation. So I just want to talk about electromagnetic radiation. For electromagnetic radiation, let's read what this PowerPoint says here. These are electric and magnetic fields propagated as waves through empty space or through a medium. A wave transmits energy, so it's energy transmission by a wave. These are waves here. Waves have certain features to them. This is a wave using a piece of string. And one of the features of waves is this thing called lambda, wavelength. That's the peak-to-peak distance here. These waves don't stand still. These waves are moving. And so this is the direction of travel here, you can see. How fast do these waves move? Waves of electromagnetic radiation, do you know? They move at the speed of light. In fact, this electromagnetic radiation is light. And these are going to be moving at the speed of light. Do you know what the speed of light is? It's fast. This is EM radiation. EM radiation consists of electric field. Now, what is an electric field? An electric field is going to have a plus and a minus end, let's say. So let's just, for sake of argument, just call this end plus, this minus, plus, minus. And this whole thing's moving at the speed of light. The speed of light is given the symbol c, lowercase, and it's 2.998 times 10 to the 8 meters per second. About 3 times 10 to the 8 meters per second. So it's moving very fast. So what do you feel when an electric field hits you, this electric field? Well, it's moving very fast. It's moving at the speed of light. And so light hits you, what do you feel? Nothing. You don't feel anything, but something's happening. Do you know what's happening?
With our body or?
Yeah, with your body or with whatever else. Well, you're a piece of matter. So how does matter and light interact?
It absorbs it.
Yeah, what in matter absorbs this? Well, or how does matter interact with light? And let's do this. Well, electromagnetic field is electro, standing for electric field. So there's a moving electric field, plus, minus, the speed of light. But there's also a magnetic field. This magnetic field you can see is perpendicular to it. And so if we have a magnetic field, and it's going to have waves, and these waves correspond to an oscillating magnetic field. An oscillating magnetic field is this. It's north, and then south, and then north, and then south. So it'd be going like this. A magnetic field, or a magnetic wave hits you, and it's going north, south, north, south. So if you're a magnet, what would happen? All of a sudden, you're north, and then south, and then north, south. So if you're a little magnet, you're going to just be going like this, crazy, because it's changing. Well, we're focusing on the electric part of it, and chemistry deals with electrical interactions. And so let's take an atom. If you're an atom, you consist of a nucleus, which is positive. And so if you're a nucleus and you see this, then you're gonna see plus, minus, plus, minus. So your nucleus, you're positive, so you're gonna be attracted to the negative and repelled by the positive, right? But nucleuses are kind of heavy. They got a lot of inertia, so they don't really interact much with this particular wave. But you know what interacts much more significantly than a nucleus? An electron. So if you're a light, electron, how much does an electron weigh? Not much, right? So if you're an electron, what are you seeing? You're seeing this. You're seeing all of a sudden it's negative, you're negative, and then all of a sudden it's positive, and positive and negative attract. So if you're an electron, you're bobbing up and down with the wave because it's positive and negative. And so this is how it's going to interact. The wave comes and the electron's going to go like this, just like the magnet would go like that. And so the electron will start to what we call oscillate with the wave. Like this. And so we're looking at electrons, but anything that's charged can oscillate with the wave. Well, how do we characterize the waves? We're going to characterize the waves via something called wavelength, which is lambda. The speed, which we call c. And one other thing. If you're this electron, like this, then you're going to feel something called the frequency of this, and that's how fast you're oscillating up and down for a second. And so the frequency, nu, is the number of up and down cycles. So let's say you're just a cork in an ocean wave. So you're at the top, you go down to the bottom, and you're back at the top. That's one cycle. So frequency is often in cycles per second or just per second. And the units for frequency are hertz. You can see it up there, hertz. Which is a cycle per second, or just a second per minute. Lambda, the units for lambda are going to be in meters, centimeters, micrometers, nanometers, angstroms, picometers. And the unit for the speed of light are the velocities, meters per second. So I rounded it. So these three things are related by this equation, and we're often interested in the frequency. The frequency is going to equal c over lambda. And so it turns out the longer the wavelength, the lower the frequency. And so the longer the wavelength, the fewer cycles per second hit you. So lower frequencies like this. The shorter the wavelength, the higher the frequency. So higher frequency would be like this. We can characterize our light. There are lots of different types of light characterized by their wavelength, frequency, and energy. So let's take a look at these. The longest wavelengths would be like radio and TV waves. If you look at radio waves, how long are the wavelengths in radio waves? They're pretty long. The wavelengths are, let's say, around a meter to 10,000 meters long. But radio, what does FM radio? What's the frequency for FM radio? FM radio is 100 megahertz, right? Because 100 megahertz, that would be around, mega is 10 to the 9th, so it would be around here. Give you a pretty long wavelength. So here, centimeters long. Actually bigger, hundreds of centimeters. And so, if you kilohertz AM radio, kilohertz would be around here. What is it, 900 kilohertz, 1,000 kilohertz? So maybe around here. So AM radio has wavelengths of around 1,000 meters long. you have a wavelength of 1,000 meters or a kilometer long, that's a long wavelength, right? Kilometer. But it's passing you, 1,000th of those wavelengths are passing you in a second to get a kilohertz oscillation. As the wavelengths get shorter and shorter, like look at these wavelengths here, you know, about how big is an atom? An atom is roughly how big in terms of meters? This is why I like this unit. I like the unit angstrom because that always reminds me how big an atom is. 1 to 6 angstroms. An angstrom is defined as
10 to the minus 10?
10 to the minus 10 meters. So an atom is about this big. So X-rays and gamma rays have wavelengths even smaller than an atom. You know? That means their frequencies are enormous, you know. And frequencies are huge. So megahertz is 10 to the 6, actually. Actually, no, megahertz, FM radios around here about a meter, so 10 meters. FM radio. But what's faster than a megahertz? Gigahertz is around 10 to the 9th. What's faster than a gigahertz? Terahertz is 10 to the 12th. Yeah. At 10 to the 12th, that's terahertz. What's faster than a terahertz? Don't know, right? Because we ran out of prefixes. And so gamma rays have frequencies of tera, which is 10 to the 12th, terahertz. They'd be a terahertz. 2 terahertzes. It's huge in terms of frequency. And so the frequency is enormously high. But we can relate all these using this equation here. Okay, now radio waves are what we call low energy. And so what we're going to do is we're going to plot these in terms of energy. Radio waves would be lower in energy. And so I don't know if you see this much anymore, but I used to see this all the time. You know, this car, they used to have these antennas, you know, the metal antennas on cars that break off. And then once in a while you see somebody driving around with a coat hanger as a coat hanger. Why a coat hanger? And then, you know, then there are people, well, metal coat hanger, maybe they could use a plastic coat hanger. Would a plastic coat hanger work? Why not?
It's metal to metal.
Metal to metal. Well, yeah, metal to metal, right. But a plastic coat hanger wouldn't make a good antenna. A radio wave, you know, this has enough, when we think about matter, this can excite electrons in metals. It turns out that metals have loosely held electrons, so as a radio wave passes by, the electrons can oscillate with the radio wave, kilohertz or megahertz. And then you get that. And so radio waves are enough to excite electrons in metals, but in plastic, the metals are, you know, if I have a plastic like this wouldn't be very good because the metals have loosely held electrons and plastics have tightly held electrons. Can't oscillate so easily. How about microwaves? Microwaves are higher in energy than radio waves. And so, have you ever put metal into a microwave?
Yeah.
What happened?
It's just the like
Sparks up.
It sparks. So maybe microwaves overly excite electrons in metals, right? A little bit too much excitement, which we don't want.
It's fun.
But mostly what microwaves are used to do is to
Then why do you like when you put oil in
interact with water.
It's just for your phone, if you put in microwave, you can dry it.
Dry? Is it
Like your phone.
Well, water is neutral, right? But in a sense, it is, overall it's neutral, but there's charges here. In water, we have a negative charge and a positive charge region. And so if you're in an electric field, you know, all of a sudden the field is negative, the field is positive, you're an oscillating field. So what's going to happen is, as this field is changing polarity, negative to positive, the water is going to be doing this. The water is going to be flipping. And we call that rotation. And so what happens is microwaves can rotate small polar molecules like water. And so it's enough energy to cause it to rotate. Infrared has a little bit more energy. Infrared can actually interact with this bond. If I look at the bond, the HO bond here, and just focus on that. So I see there's a positive and a negative end. And so what happens is if the wave comes in, the wave's positive, negative, what happens is if the wave has enough energy, it can excite the electron. So there's more what we call electron cloud or electron density over here, and the electron density moves and the bond starts to vibrate. And so water is good at absorbing infrared. You know that? Water is good at absorbing infrared, but nitrogen's pretty worthless. Nitrogen doesn't really absorb infrared very well, or oxygen. Oxygen's not good either, absorbing infrared. Do you know why? They're not polar. These are not polar, so these are kind of invisible. And so this is it. You know, this room is filled with nitrogen and oxygen. Nitrogen and oxygen are what we call non-greenhouse gases. You know, this room doesn't heat up unless, you know, have you ever gone into a hot room? You know, there's a window out there. It's not because of nitrogen and oxygen. It's because, well, it could be because there's kinetic energy as well. I mean, translational kinetic energy. And so nitrogen and oxygen can heat up, but that's not what we call a greenhouse. If that room was filled with CO2 versus nitrogen and oxygen, that room would be a lot hotter. Right? If that room were humid, it would be a lot hotter. If that room was filled with methane, it would be a lot warmer, probably. Yeah, methane's a greenhouse gas, too. And it's because of this, you know, the vibrational energies. The nitrogen and oxygen doesn't, you know, so that's a cold day out, right? And you're in the shade. And you know there's a shade and sunlight? And so let's say you're standing in the shade and you put your hand out in the sun. What do you feel? Do you feel heat or do you feel infrared? If you felt heat, then the nitrogen and oxygen molecules are hot, transferring the energy to you. So in the shade it should be hot. In the sun it should be hot. In both places it should be hot because you're looking at kinetic energy and nitrogen and oxygen, right? What you're feeling is infrared. Infrared. And so the infrared comes in here and starts to vibrate.
Professor, isn't that kind of how it was discovered? They measured temperature in like sunlight, and then there was like a higher temperature, like to the right or something. But they couldn't explain why. That's how they discovered infrared.
Well, I had such a brilliant program on infrared in which it showed the little cartoon guy Lord Fahrenheit or something, walk out from the shade into the sun. And they had this little animated thermometer go up. But, you know, gosh, I got that from, I got that program from one of the largest manufacturers of infrared spectrometers. But it was too old and it was never updated, so it doesn't work on modern computers. But I'm going to take a look and see if they posted it online somewhere. But yeah, there's something similar to that. I don't know what the whole story is, and I always wondered why they had some kind of ancient guy do that, but it must be because of what you're talking about. What's so what infrared does is it causes vibrations. It causes bonds to vibrate. So we got electrons and bonds. We got, you know, for microwave, we got, you know, what we call non-symmetric or asymmetric electron distribution. And then we have visible light. You know, infrared, microwave, and radios are invisible. The visible light we can see, white light, rainbows, whatever. For visible light, what does visible light do? Visible light excites electrons and matter. So it just causes these electrons to get excited. It causes the colors. And then we have UV. UV is enough to break bonds. That's the damage that UV causes. Here with infrared, it just vibrates, but it doesn't break it. But with UV, it's enough to break the bond, cause chemical damage, so it breaks bonds. Then we get to X-rays and gamma rays. X-rays and gamma rays we call ionizing radiation. It's called ionizing radiation because it's enough to excite the electrons so much that once the electrons get too excited, they knock off matter. And so when the electrons get knocked off matter, it creates ions. So we call it ionizing radiation. And so it excites electrons in most matter enough to ionize it. All right. What you should know is I don't expect you to memorize the wavelengths and frequencies of any light, except for one. You need to know visible light. One, do you know the colors of the rainbow? Yeah. Roy G. Biv. Yeah, red, orange. Roy G. Biv. Everybody knows Roy G. Biv? Okay. All right, then at the end of red.
You said orgy biz?
Roy G. Biv.
I was like, what? I didn't know what you said. Sorry. Like, what?
All right. Well, anyway, you should know that at the edge of red is 760 nanometers. So that's a wavelength. 760 nanometers. Beyond red is what we call what? Infrared. Infrared is like what, 1,000 nanometers, roughly? 1,000 nanometers is called a micron. So infrared, we have micron or micrometer wavelengths. And so infrared micrometer wavelength, visible, 760 of red down to 390 of violet. And so a visible light ranges from 390 to 760 nanometers. are roughly 400 to 800 nanometers. What's on the other side of violet? Ultraviolet. Ultraviolet has wavelengths on the order of 10 to hundreds of nanometers. So like 100 nanometer wavelength would be ultraviolet. 50 nanometer wavelength would be, no, it's still ultraviolet.
What's the smallest wavelength ever observed?
So ultraviolet is like
I don't know.
not as strong.
But can it go like infinitely?
No, it can't. It can't because you generate there's a limit to how much energy you can get. I mean, it'd be just an enormous amount of energy.
So there's energy behind
Oh, so it's
the wave.
going.
You know what you're saying?
Okay.
There's energy not behind the wave. The wave is energy. Yeah, that's
So
how
ultraviolet
energy
is
is
like anything
transmitted.
besides 390, below 390.
Below 390 is ultraviolet, but you can't go too far below. Because ultraviolet is going to be, well, a nanometer, hundreds of nanometers is 10 to the minus 7 meters. And so we go around 10 to the minus 7. Ultraviolet just goes down to about 10 to the minus 9. You know. But you just know that visible is very narrow, but you know that these vary several orders of magnitude. So 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. Wavelengths vary several orders of magnitude. The visible doesn't. And so normally we think of infrared. They have this. They have something called the near infrared. Have you heard that? The far infrared. And it depends on where you are. The near infrared is near visible. So this is near infrared. This is far infrared. This is for space. If you listen to space talks, they talk about near infrared and far infrared telescopes. Right? If you talk about sunscreen, they talk about UVA, UVB, right? That depends on what part of this you're at. Are you in the UVA region or the UVB region? And so they subdivide it into little categories here. X-rays, the same thing. Gamma rays are going to spread. Uh-huh.
So is it just the speed of the wavelengths that excites?
Not the speed of the wavelength. You wouldn't call the speed of wavelength because that might get mixed up with the speed of light. The speed of light's constant in the vacuum, right? It's the frequency. Yeah. So in other words, this high energy has high frequency. These are all high frequency light. High frequency, the electrons can be oscillating like crazy, or whatever is oscillating like crazy. High frequency has very short wavelength. Okay, low frequency has long wavelength. That's it. And so red light, is it lower in energy or higher in energy than violet? Which one has higher energy? Red or violet? Violet has higher energy. Red light has lower energy. And that's because there's an inverse relationship between wavelength and frequency. Frequency is directly proportional to the energy. When we're dealing with light, this is, those little spectroscopes you have? The way it separates the colors of the rainbow are by using this interference of waves. When you have two waves interact like this, you'll see some kind of interference pattern like this. This interference pattern is generated when the waves are in sync versus out of sync. When the waves are in sync like this, the peaks match, the troughs match, we get something called constructive interference. Constructive interference, the wave just grows in amplitude here. Whereas if they're mismatched, let's say this peak is matched with the trough here, these are 180 opposite, then the waves cancel. But they don't even have to be 180 opposite. What they could be is just slightly mismatched and the waves will cancel. And that's destructive interference. And so that's how this works. Inside those little spectroscopes, you have something called a diffraction grating. diffraction gratings like these CDs, there are a whole bunch of grooves there. And those grooves, you know, depending on the angle, you can get constructive and destructive interference. And depending on the angle you put it, you know, a slight mismatch, all those will cancel out. The only one that matches is the one, that color that you see. And so depending on the angle that you look at, you'll see one color. That's a diffraction grating. We also have refraction, which changes, you know, the speed of light changes through the medium that you have, and it impacts some wavelengths more than others. And so here you can see, we could spread out white light, which has all the colors in the rainbow, into Roy G. Biv here. This is, in the spectroscopes you have, we don't have prisms in there because prisms are expensive. Diffraction gratings are cheap. You could get refraction using droplets of water as well. The same kind of principle here. Well, when you make a light bulb, what do you want? You want all the colors of the rainbow, right? That makes a good light bulb. And so here, we could make a light bulb out of many different materials. This is, this would be a light bulb here because do you see there's white light coming off here? White light should have all the colors of the rainbow, like the sun. It looks like there's white light coming off these, but is it like the sun, the solar spectrum? No, it's different. This would be more closely like the sun. But would this be a very useful light bulb? No, that would be a pretty bad light bulb. But it's molten iron. Why does molten iron act like a light bulb? What's giving off that light? It's electrons. Molten iron has electrons, and in molten iron, there's a lot of kinetic energy. Those electrons get excited. The electrons don't stay excited forever. Eventually, the electrons will calm down. When the electrons calm down, they release energy to the surroundings. When you release energy to the surroundings, you can release it in the form of heat and the form of work. Is light heat? No, light is work. And so we're releasing that energy, and in this case, it's a very efficient conversion into light. And so the electrons get excited. But you know, in molten iron like this, some electrons are a little bit excited, some electrons are a lot excited. And you don't have just one excitement level. You have a distribution of excitement levels. And that means that we're going to get the full rainbow because the electrons that aren't that excited will emit in the red. And actually, you know, molten iron also emits in the infrared too. And so you'll feel the heat from there. And then the really excited electrons will emit in the violet. And if you continue to excite it even more, it should start emitting in the ultraviolet as well. And so, let's see. So but this is not a practical light bulb. And so the light bulb, like the ones that we used, the one we used yesterday was tungsten, which is a metal, and we don't have to melt it. And so, you know what? I'm going to try to make a light bulb out of the spatula.
If you continue to excite the iron, would it emit like X-rays and gamma rays? Or no?
In theory, yes. In reality, no. Well, let me say, you know, that's how you generate X-rays. We generate X-rays like in a lab. If you want to generate X-rays, you have a copper filament, and you excite the electrons. But in this case, you excite them a little differently than what I'm showing you here. What I'm showing you is this is what we call black body radiation, which is anything with electrons we can excite to get to emit. Copper is special. Copper, you excite the electrons in a certain way that you knock an inner electron out, what we call inner shell electron. Outer shell electron drops back in and starts emitting X-ray. So we only emit a certain frequency of X-ray by using copper. It's called copper K alpha, is the X radiation that we use for that. And so this is why
When I used to work with X-rays, and I used to work with X-rays quite a lot, we carry around an X-ray badge. You know, X-ray badge. X-ray badge is. I didn't like X-ray badges because once a month you turn in your X-ray badge, and then they, which is just a piece of photographic film, and then they see, wow, you've been exposed to too much radiation this month. You should take the next month off. You know, but I don't want to know a month later. I want to know if I'm being exposed to too much radiation, then I'd like to leave the room right now and not wait a month, you know? And so I thought, my God, I didn't like that. I thought there's got to be a better way of doing that.
So you were exposed to a lot of X-ray?
No, I wasn't, but, you know, if something happened where the shielding was down, or, you know, I didn't know X-rays were being emitted or something else, you know, you can't see them, probably can't feel them so much. You might start getting hot. But
What kind of metal is it?
stainless steel,
Oh, it's
any metal will do.
really-
If I keep heating this up, what's going to happen? Well, first it's going to start glowing red, right? Well, first it'll start glowing infrared, but you can't see it. You know, you can feel it, though. I can feel infrared. And then as the electrons get more excited, it'll start glowing red because, you know, most electrons are excited. So I'm getting red and infrared.
It'll go white.
Yeah. And so I want to continue to excite these, and then what's going to happen? Eventually it's going to start going orange and then white eventually as the colors add up. And so this is essentially the operation of a light bulb. You just got to heat up the metal until it gets, well, in a light bulb we don't use a flame to heat up the metal. Do you know what you use? Electricity. You use electricity to heat up the metal. You get the electrons excited, they're going to start emitting all colors of the rainbow, which is going to give you white light. And so what this is you know, basically, I'm using stainless. Stainless is fine, but if I use tungsten or iron, you know, it would oxidize. It would react with the oxygen in the air and form iron oxide. Iron oxide is very brittle, start to break. Stainless is okay. Well, I'm not going to heat this long enough to get it white hot, but eventually the concept is all we have to do is excite the electrons, and then we can, well, anyway, the time. Excite the electron, we can make a light bulb. And so let's try to make light bulbs out of different things. And so this is what we're going to do. We're going to try to make a light bulb out of everything and see
So Edison
how that
did
works.
Or Edison tried that.
And we'll do that next time. So I'll stop now.